Welcome back to the EXD. By the end of this video, we are going to understand how a user input is tokenized and embedded before being processed by an LLM. We'll get an intuitive sense of what the inner world of an LLM looks like, what the manifold hypothesis suggests is going on inside these beasts. My name is Ram and I work at the Ethereum Foundation on AI Ops. And this is an open learning log that I call the EXD. To start at the beginning, check out episode 1. I'll link it in the description below. Okay, let's start. This is going to be fun. We have already looked at the anatomy of an LLM inference pass. So we know that user's text input is first tokenized and then it goes through two phases, prefill and decode, before the text output is returned to the user. And today's video starts a deep dive on each of these high-level sort of chunks that we have revealed by peeling the first layer of the LLM onion, and that's tokenization. So let's get into it. This is going to have some interesting insights, some of which surprised me actually. So tokenization and this thing called embeddings, we're going to understand what this is. And the question we're answering is, how does a sentence which the user inputs become a list of vectors? And what does that space actually look like? We'll know what we mean by this. And for this, we'll use our actual tokenizer that we're using with our model, because in the EXD, we like to work directly with sort of the cutting edge technology right now and use it to understand what we're doing itself. So these are the sections. There's a quick setup section. We'll take a very quick look at the full pipeline, how text is tokenized, and then it goes to prefill, decode. It gets detokenized. We don't need to look at that, and then returned as text, just to get a quick reminder of the whole process. Then we'll talk about how text first becomes tokens, and then tokens become vectors. And this is the small step that actually I sort of could have realized, but I just preparing this video made me remember that text, token, and vectors are actually three things. It's not just text and tokens. Finally, we'll take a look at the embedding space and get a sense of what this manifold hypothesis is and what the inner world of an LLM could potentially look like. Okay, let's get started. So this is just a standard setup cell. What we're basically doing is checking if all our required libraries are available and everything seems to be okay. And we have access to CUDA, which we'll use for tokenization on Yoneda actually. This we're not talking about Atom over here. Okay, setup looks good. Let's take a quick look at the pipeline. So the first thing we're going to do is load Qwen's tokenizer. And a tokenizer is basically the piece of the model that actually converts text into tokens. So we've loaded that. And what we see here is that we're printing out two things. We're printing out the vocabulary size and also showing some of the special tokens. So the vocabulary size of the Qwen tokenizer is 248,044 tokens. So this means anything that we enter in actually multiple languages is represented by these 248,044 tokens. So you can imagine there are some of which are in fact these special tokens. So these are the kind of tokens that signals to the inference engine that the model is done with the answer, for example, or maybe here's some audio starting, audio ending, image, vision start, vision end. These are the kind of special tokens. But essentially what we're saying is you can imagine all the words in the English language, right? Like absolutely anything that you can enter into and send to an LLM, it will get represented by these 248,000 tokens. Let's think about this for just a quick second. We could have, for example, reduced this vocabulary by saying tokens are characters, in which case it literally is the entire character set, right? Like the alphabet, the numbers, and all the special characters. And maybe that's just a couple of hundred tokens long. And that could have been the vocabulary, and then maybe what an LLM does is it emits its answer character by character. But that was found to be inefficient. And that there's actually sort of a middle ground. The other end of the spectrum, for example, could be to try and list every single known word in all the languages that the LLM is aiming to speak, which would run into millions of tokens. So tokens are actually a sort of middle ground where it's not as fine-grained as literal characters, which, if you think about it, just represent the phonetic structure of a language, right? The only sense that a character makes in a language is a sound that is associated with the character. But LLMs, the field of machine learning, discovered this sort of intermediate representation of tokens, which we'll take a closer look at. Okay? So what does that look like? Well, the first thing, and this one sort of took me not by surprise, but I just never thought about it, and you see it here. I have a prompt. Gentrification is a complex and multifaceted process with a space, kind of suggesting that, okay, continue this sentence. So that's going to be our prompt. Let's encode this prompt. Here we're taking the tokenizer, which we loaded over here, and we encode it. And let's take a look at what happens when you do this encoding step. What is encoding? We'll print these out. So here you go. And here we see something interesting. The word gentrification is split into G, ent, and ification. But is and and this funny symbol ahead of them actually means this is with a space before it, actually. And this is with a space before it. Words like complex and, they all get their own specific tokens. Maybe they're just common enough. But once again, multifaceted is actually split into multiple tokens. So it's multif, as or ac, and etid. And then process. And then here you see that space gets its own token. So this is actually how these tokens are being split up. It's quite interesting. And I imagine that this was happening in a neural networky kind of way, and that's what surprised me. Let's take a quick look at in this section we'll see how these tokens are actually created. Okay, so actually what happens is this sentence, 1, 2, 3, 4, 5, 6, 7 word sentence, gets split up into these 12 tokens, counting from 0 to 11. And actually the LLM is sent these 12 tokens. Okay, let's send it to the model and just for completeness, see it print out a result. Okay, so the output is, and here I've restricted the number of tokens that can come out to 8. So basically this is where our sentence this was our prompt. Gentrification is a complex and multifaceted process, and these are the 8 tokens that it emitted. Okay. All right. So yeah, this is pretty much a quick picture of how a prompt, a piece of text, is broken up into these tokens and then sent to the model for an answer. Cool. Let's look at how this actually happens. Okay. And this is kind of interesting. The goal of tokenization is vocabulary compression, not to the extreme limit, which is find the smallest number of tokens that can represent everything in a language, but some sort of semantically useful level. And in fact, if you go back or we can discuss it later, but some sort of semantically useful level so that the LLM is not sort of processing our words character by character. And if you think about it, we don't either, right? When we we don't know what actually happens inside our heads, but it feels like we don't, when we hear somebody say a word to us, like say parrot, we don't think, oh, Parrot, that represents, we instantly like sort of absorb the word itself. So you kind of have, a sense of what a useful token is. So let's look at this set of words: transformer, revolutionized, NLP, embedding, and attention. We have purposely sort of chosen slightly more complex words, which perhaps don't form what you could think of as the base of a language. Let's see what they look like in token form. Okay, this is interesting. Transformer gets split into two tokens, transform and Revolutionized gets transformed into revolution and ized. NLP, which is, could be one of millions of acronyms, is N and LP. But embedding and attention get their own tokens. So you're already beginning to get a sense that, it's useful to split words into their base forms and their modifiers, right? So transform is a base form, and transformer is a thing that transforms. So, or a revolution is, this great transformation, and revolutionized is what you call something that has undergone this revolution. So how is this done? How does Quen do this for any potential word that you may send its way? Turns out it's actually statistical. This is what surprised me. I actually thought that this was, a learning kind of process, and it kind of is. But actually, it's more statistical than machine learning. Yeah, and we're going to see that. We'll do this by actually implementing what's called byte pair encoding. That's what we call this. So this is the kind of tokenization that GPT-4, Claude, and all these modern Quen models use. So we'll do it with a very tiny training corpus. So our results will not be, precisely what happens in the real world, but it'll give us a very clear sense of what's happening. Our corpus is a set of words that are like this: play, player, players, work, worker, workers, teach, teacher, teachers, etc. So obviously you can see that our goal is to actually kind of see if we can mechanically get the base forms and the modification, how well it can, a system can do that. So that's what our corpus is. We set the corpus up. And then we basically start by splitting the vocab into letters. So we literally just split the whole thing into its letters. And by the way, this is each of these in the corpus, each of these sentences or sets of words have been multiplied by 5. This is just to give enough material to do a series of rounds. That's a detail that we don't need to worry about. Okay, so we start by getting a very base vocabulary to split literally into individual characters. Then we find all the pairs that appear most frequently and we merge them. So if we keep finding that ER is appearing together, then we merge E and R instead of having them separately as E and R. If we find EST happening, ES happening, then we do that. That's what this function does. And then we keep merging the winning pairs. And that's it. This is actually a completely mechanical process. Kind of took me by surprise. And if you run this goes through this process. Here we have gone through 40 rounds. And let's look at the words that come out. There's one thing we'll do. We'll remove... okay, let's just see what it looks like and then I'll explain. So, interestingly, great, which is not a neat 4-letter character, got split into grey and t. And greater got split into gria and ter, which is kind of interesting. Let's see and it could be because of the existence of short, shorter, shortest, right? This kind of goes to show that this is not exactly a semantic tokenization. It's actually a statistical one. This is the important takeaway from this. So in the first step, we just do the way in which the vocabulary is constructed is in this way. And this can be done ahead of time, right? You don't need to, this is not actually happening each time. This is the way in which you construct the vocabulary. And once you have the vocabulary, it's just a matter of a lookup table to find the token that represents a piece of text. This is pretty cool. I did not know this. And it does a great job of actually identifying tall, taller, teach, work, and actually identifying all of these. But interestingly, for example, here, it's able to split workers and work, but it did not find worker. It didn't split work into work and worker. That's of course because this is just a toy example. Cool. So this is our first sort of insight. Tokenization is a statistical process whose goal is vocabulary compression, and that too not from a semantic perspective, but actually from a functional perspective. Useful chunking of your text so that the LLMs can then do their own magic on it. Okay, that's the first takeaway. Okay, but if you notice, all we have done now is figure out how to split the token. But we're not yet reached the stage where we're talking about how it's represented inside the LLM. It's not as if, there's not a big difference between an LLM being able to see a word and LLM being able to see a part of a word. Actually, like we mentioned in our previous episodes, what it actually sees are numbers, or more specifically, vectors. That's actually what an LLM works with. So how does that work? So each of these tokens actually maps to a token ID. So there is an embedding matrix, and we can actually download this. In fact, it's part of the model files. It's actually a part of the model itself. And we actually just download this shard from Hugging Face. It belongs to this model. And what we do is we print out the shape of the matrix. Okay, so what we're doing is we're getting this lookup table that tells you how the token ID maps to the embedding matrix. Let me just go back 1 second over here. Yeah. I just realized that I have not actually shown you the token IDs themselves. I've shown you the tokens, but each of these is actually associated with a number. So let me just pause this and just bring that in and show it to you. Okay, we're back. I just quickly added a 2.0 cell here because I realized that while we had shown how tokens chunk text into different pieces, we didn't actually show that each of those tokens are then given an ID. So let's quickly take a look at that here. Let's collapse this. So in this section, we saw how the tokens are chunked, what the logic is. We saw that it's a purely statistical process. So in 2.0, let's just look at these set of tokens. Each of these is actually represented with a list of token IDs. So for example, embedding, which is just one token, has the ID 91342. But transformer is represented by two tokens, 4549 for transform and 261 for Similarly, revolution and ized are represented by these two tokens, so on and so forth. So tokenization is token and ization, right? And this makes sense because ized, revolutionized, frigidized, or transformer, worker, teacher, right? So you want to have teach and so text or word, subword tokens, each of which are then represented by token IDs. Cool. So what does the LLM do with this token ID? It just looks it up. So here we're downloading the actual embedding matrix from the model weights. That's actually part of the model files that you download from Hugging Face. And what we're going to look at is what is the shape of the embedding matrix, and And let's just quickly run that. So it's 2,248,320, that's 248,320 tokens in 2048 dimensions. So this means that a single word like the is actually a point in a 2048 dimensional space. Okay? If you've come so far in this video series, this should not be something that's too crazy for you to imagine. We understand how to represent data in two-dimensional spaces, in three-dimensional spaces, and it's just a direct extrapolation to think about 4, 5, 6, 2048 dimension spaces. And all it means is it's a string of numbers with a string of numbers 2048 elements long. That's pretty much what each token is. It's a point in this embedding space. Okay, and we can see that actually the embedding type is float 16. This is sort of the standard floating point representation of a number with 16 places of precision, this is very relevant to future subjects like quantization and stuff. But yeah, so this is what actually happens. So let me just repeat this because this is what it's important to understand. In fact, let me find a visualization for this. Each token, over here, like embedding, the whole token for embedding or attention, or transform and will be 2 points. Each of these are a point in this 2048 dimensional space. This is the number of points in that space. This is the dimension of that space. Okay? And this is kind of what it looks like. There's something that one of the founding fathers of this space said. He said, the way to think about higher dimensional spaces is just imagine a three-dimensional space and just think this is a higher dimension. That's it. Okay, don't worry about it. And there is a hypothesis that's what's actually happening during the training phase of an LLM is that it's taking tokens, because that's what it's fed, and fitting them into a manifold. A manifold is kind of a smooth, continuous surface in a high dimensional space, right? Kind of like this. This is a manifold in two-dimensional space, kind of. And that's what it's doing. It's taking all these points and kind of peppering them and placing them on this so that this space is formed by all the points. So it's actually all the points kind of fit on this kind of a space in 2048 dimensions. This is kind of crucial to sort of get in your head that this is what is happening inside an LLM. Okay, let's go back and continue to think about this. This is the space, and so these are 248,320 tokens, of which many tokens are there's 276 tokens, which are actually alphabets and digits and stuff like this. 276 are actually special characters, and 248,044 are the number of other types of tokens. Okay, so every token ID 91342 for embedding, for example, is just an index onto this table. The model can just look it up and pull the point on this crazy structure inside its brain and say, that's what you mean. You don't mean embedding, you mean this point over here. Okay, that's what's happening. Embedding is this point. Revolutionized or revolution is this point. Ized is this point. Teach is this point. Is this point. That's what's happening inside. Okay, excellent. Let's take a closer look. Let's pull a few tokens and look at their actual vectors. Now remember, This is a list of 2048 numbers. So we're not going to see all of it. Okay, we'll just pull the first 8 dimensions. So the word the, or I should say the token the, which has the ID 1719, is actually this vector. So it's a point, it has negative and positive coordinates. All of them are actually compressed within, I believe, 0.5 and plus 5, or 0.05 and plus 5. Quen compacts the vocabulary space, probably for performance reasons. So complex is this other number, process is this, has this ID and has this vector, city is this, and so you can see that this is basically what's happening. Okay, so user starts with text. That text is chunked into tokens, which are actually determined through a purely statistical method. And then those tokens are associated, each of those tokens, which could be subword pieces, are associated with points in a higher dimensional space. So once again, transform, revolution, iced, teach, walk, etc. Okay, cool. Let's keep holding this in our head. It's kind of hard to see what this even means. Let's take a look at it as a heat map. So this is all the 2048 dimensions in a heat map, and it goes from minus 0.05 to plus 0.05, so it compresses it into a unit 1 size, and there are, I'm sure, many optimizations that take advantage of this. And as you can see, some of these things, for example, look at the word complex. Now, this is also maybe a good point to talk about the EXD way of doing things. What we're doing is we're taking actual working code and kind of like, this is the equivalent of like unscrewing the casing of a clock and starting to look at the gears inside, right? Like we're just directly looking at the actual embedding, Quen embedding of the term complex. Now, the first question is, do you see something interesting here? Each of these strips represents a dimension in the multidimensional space. And if you look at this token for the period, what do you notice? It's mostly empty in most of those dimensions. And as you can see from the legend here, it's quite close to the origin. The lighter colors are lower numbers. So, interestingly, the vector for the period appears to be a point which is very close to the origin. And you can imagine that points, commas, and other such words are very tightly clustered around the origin. Okay, let's look at and, which is another very common function word which is very useful and can be used in a variety of contexts. It doesn't have so many colors. It is also lightly colored. It's pretty strong in some dimensions, but not so much in others. Now compare these two with something like complex. Look at that. If you imagine this in your head, these are points which are far away from the origin and which are like not just lying on any one of the planes, right? So let me just pop back to this visual over here. You can think of, like, 0, 0 being here, and all the simple function words, adjective, pronouns, periods, punctuation to be close to the origin. And more complex words appear to be further away, and not just that, they don't sit on one plane or the other. They're actually represented they have values in all the dimensions. It kind of suggests very intuitively that it takes contributions from all of those dimensions to provide the meaning for this word. Whereas the period, which maybe has, in a sense, very little meaning compared to something like complex, or very few dependencies, does not seem to take as much dimensionality to represent it. I think this is really cool. The fact that we can actually see this by kind of peeking inside is really cool. Look at process. It's got, much like complex and like city, it has a lot of representation in different dimensions. Interestingly, it does seem to also have a lot of dimensions, but less so. And you can kind of see a process here. Simple words seem to be quote unquote low dimensional. Most of their values in many of those 2048 dimensions appear to be 0, and even the magnitude of these vectors seems to be quite small, whereas more complex words get represented by more, it takes more dimensions to kind of represent them, and their magnitudes tend to be high, so they're kind of further away from the dimension. This is awesome. And how are these points determined? This is actually what happens during training. That's the idea. The vector is learned during training. And this begins to give us a sense of what is actually happening inside an LLM during the training process. We'll come to that later, but you can think of all the tokens being just distributed like a gas through this 2048 dimensional space before training. And as it goes through the training process, that gas is slowly, all the vectors are nudged and tweaked and pushed until it starts looking something like this. And this is what is called the manifold hypothesis. That what an LLM is actually doing during the training phase is it's by constantly being given examples of sentences and their continuations and trying to curve fit, it actually starts generating this manifold inside the space of its mind that looks like this. And what we've seen so far is kind of compelling. It suggests that that is in fact the case. I think that's totally amazing. And the fact that we can just kind of get a sense of it from Python is really cool. Okay, right. So words are chunked statistically into tokens. Tokens are then actually given points in a sort of model inside the mind of the LLM, so to speak. They're given points in this vast 2048 dimensional space, which kind of are very interesting. But why? How does it, what's kind of like the rationale for applying a single point to a specific token? The question that we're asking is, do tokens that appear in similar contexts contain similar vectors? Right? You imagine that cat and cats, well, the question is, are those 2 points far away from each other in this higher dimensional space, or do they actually lie very close to each other? Let's find out. So let's explore this embedding space. Now the problem is, of course, that we can't see or think in 2048 dimensions, right? So we're going to have to sort of use a dimension reducing algorithm. What this algorithm basically does, TSNE, it assumes, I think, a t distribution and then uses probabilities to project high dimensional spaces down to lower dimensions. And its goal in doing that projection is actually to preserve local neighborhoods. Okay, this is an algorithm that tries to preserve local neighborhoods. This is very cool. You should, I'm not going to go in depth into how it works here. It's actually fairly simple actually. But this is what you need to understand, that basically that's what it does. And what we'll do is we'll take these 2048 dimensions for a set of tokens and we'll project it down to 2 dimensions. And because this is neighborhood preserving, it actually can show us a sort of sense of the structure of this embedding space. Okay, so we're running this on what we did was we sampled 3,000 tokens from Quen's vocabulary of 248,000. Okay, so we sampled 3,000 tokens from there, and so this is totally random, by the way. I'm not like specifically chosen ones that will support my claim that similar tokens will be similar. And let's take a look at what that looks like. I think this is kind of glorious. Instead of seeing like a diffuse gas of random particles, what we see here is a lot of structure. It's pretty clear that, there is something about these pieces that's over here. In fact, so this color, which you can clearly see seem to be arranged in these concentric rings, are subword pieces. You can see that, in fact, all of the tokens kind of seem to belong to some sort of a ring, more or less. There are, of course, some outliers. There's a suggestion of an outer ring over here, which would just be a function of the 3000 that we sampled, by the way. You can't see this very clearly, but things like the empty tokens and the digit tokens are actually clustered in here. I don't know if it's possible to see this. Yeah, it won't really be very easy. Okay. And it so happens that when you do this kind of a projection, it's most likely, if you get concentric rings, it suggests that the population from which was projected down to this is actually a hyposphere. That's what it actually seems to suggest, which would make sense, right? The idea is it's a surface, and it's a closed surface that's connected to each other, which means, all the words in the language, all the tokens are sort of actually, in a sense, next to each other. There's you can get from one place to the other by passing through other tokens. Yeah, this is kind of awesome. But let's verify this, right? Like at this level, we're just making a claim about all the tokens that we sampled, some 3000. Let's instead do this again and look at some specific tokens, okay? And let's look at what we consider neighbors in this kind of a space. And it's also kind of underlines why it's important to understand that a token is actually a vector. Now, if you remember linear algebra, the point about a vector and its main difference from a scalar is that a vector not only has magnitude, which is kind of the length of the vector, but it also has a direction. And in this kind of a directional space, the way we measure similarity is one way that we measure similarity is using cosine similarity. It's just literally the cosine of the angle between two vectors. And so if two vectors are pointing in exactly the same direction, you'll get a cosine of 1. And if they're pointing in opposite directions, then the cosine is -1, right? And if they're perpendicular to each other, which means they are kind of unrelated, remember, same and opposite are still related. It's just that one is negatively related to the other. Perpendicular could mean it's totally unrelated, right? So this is the way we measure cosine similarity. So just remember, each token is a point, or more specifically a vector. So imagine a line from the origin going out to this point. So two tokens are actually two lines. I know I've been showing you point depictions, but actually think of them as lines. And what we're measuring now is the angle between these two lines and seeing, how closely pointed are they? Are they kind of pointing to the same meaning? Okay, let's run this. Take a look. Okay, so this defines the function that we're going to run, and then runs it. Okay. So we're finding all the neighbors of the term the here. Okay? And this is really interesting, very cool. So look, our algorithm basically found all the tokens from a sample which had a similarity to our input token. Okay, so neighbors of that's what we're doing. Okay, so nearest neighbors calls this function, and this is the token string. right? So look at what it's found. It found this the with, I think this might represent a space, this represents some other special character. It found basically variants of the, but then it found DIE, which is German for the. Oh, sorry, this is the decoded string. So this is greater than the, this is quotation the, this is n the, this is probably space, maybe there's a backslash here, the. But then it also found the German word for the, which is DIE. It also found the Spanish word for the, which is la. And it found Spanish word la with a space before it. This is incredibly cool. It actually found the word for the in other languages, purely using cosine similarity. Let's see what it does for ing. This is very cool. It suggests a different kind of semantic structure. ing, which is the suffix for many words, right? So beginning, ending, furthering, etc., is closely related to other suffixes like turned, ed. So fixer, fixed, fixers, fixes, fixation, fixating. This is incredible. There's actual similarity here. And as expected, the word run is closely related to runs, running, runs, ran, running, etc. This is, I think, pretty neat. We're not setting this up. We're using Qwen's actual vocabulary space, its embedding matrix, taking random points from it and actually doing sort of experimental science on it. We're pulling terms and seeing how they're related to each other. Okay. Now what we're doing is we're testing these sets of tokens, the with a capital T and the with a lowercase t. Run, walk, ing, ed, the and fox, for example, which are kind of unrelated, or low and high, which are related but opposite. New and old, which is, again, opposites. And once again, you can see it borne out. The and the are highly similar, 0.6. Run and walk, interestingly, are not that similar, but ing and ed are fairly similar. But things like the and fox are quite unrelated, 0.02, right? So this is very, very interesting. Okay. Finally, let's just actually look at where these words land in that TSNE plot that we looked at before, and also verify, just get a sort of a visual sense of how these points are distributed. So let's do that. Sometimes these words all sit on top of each other, so you can't actually see them very clearly, but hopefully it'll be somewhat intelligible. Okay. So immediately you can see that the numbers, so if you look, we gave it 0, 1, 2, 3. All of them landed here in a tight cluster. A and the A and tightly clustered in this entire space. Jump, walk are on different rings. Run is somewhere else. Okay. I think this is a good place to stop. We've actually spent a lot of time, but let's quickly sort of recap, because I think this was a big conceptual episode where we kind of got a deep insight into how this magic kind of works a little bit. So we did a quick setup. We saw our first pipeline where we just took some text, tokenized it, pre-filled it, and got some piece out. We understood that the way you go from text to tokens is actually purely statistical, which was very cool. I did not actually know that myself, or I'd never thought about it. Then we asked the question, okay, we know how to break text into useful chunks for LLMs to use, but how are they actually represented inside the LLM? And we got introduced to a very cool 2048 dimensional space, which kind of looks like this. it's this kind of surface inside this space. We saw that already just from this very simple sort of depiction, that things like periods and probably commas and other punctuation are sort of very low dimensional and kind of clustered at the center, suggesting that it doesn't take a lot of dimensions to represent them. Whereas more complex concepts like complex itself or process are not only far away from the origin, but also require more dimensions to sort of describe them, to place them. Very cool. Then we did some explorations of the embedding space. We saw that because we can't look in 2048 dimensional space, we projected it down to 2 dimensions, and we got a sense that yes, actually the points are distributed on something that kind of looks like this. In fact, a high dimensional sphere, a completely connected surface where language can sort of move from one place to another. And most of the points are here. And finally, we actually verified that, listen, are similar words neighbors of each other? So not only do we know that the points are distributed like this, but we also verified that maybe the is here and D and la are points which are quite close to it. Very cool. This, and then we finally kind of took a look at clustering, and we saw that, yeah, this is in fact the case. And this kind of gives us a very hand-wavy, intuitive sense of what an LLM is doing. Once it kind of finds the shape of human thought, of thought itself, then it seems to be saying that, okay, you can think of an input string as a collection of points kind of distributed across this thing. And it's what the LLM needs to do is, given a set of points on this space, it has to guess, and you can even imagine this being like just draw lines between them, right? So some sentence could be, gentrification is a blah blah. So maybe this is kind of shape. And what it's saying is, okay, given this shape on this manifold, what will be the most likely next token? That's what the LLM is doing. It's saying, given the space and given this set of points on the space, what's the likely next point on the surface that I should give back? And that kind of gives us a very tantalizing, intuitive sense of what is happening inside an LLM. All right, this has been a long one, but I think hopefully a fun one. We still have a lot more to explore inside this embedding space itself, so let's get back to that next week. Cheers, guys. See you next week in part 2.